Hello everyone, my name is Abraham Paul. I'm a first-year MTech Computer Science Engineering student at Christ University Kingery campus, and today I'll be discussing about Software Project Management, MTCS 134, which is a subject which I have for my first semester at Christ University Kingery campus, and the professor who is teaching the subject is Dr. Ganesh Kumar R, who is an associate professor at Department of Computer Science Engineering at Christ University Kingery campus. I just want to thank Dr. Professor Ganesh Kumar Sir for preparing the course material as well as the slides so that we'll be able to learn these concepts and actually do some real-world project that would help in successfully managing large-scale software project. Okay, now let me get started and talk about the first unit and also discuss about the overview of these concepts which are taught in this subject. So let's get started. So, Software Project Management, MTCS 134, course objectives are the following. This is the goal of the course. What's the main objective? The aim of the course is, there are 3 points, okay? Understanding the specific roles within a software organization as related to project and process management, understanding the basic infrastructure competencies, example can be process modeling and measurement, and understanding the basic steps of process planning, project management, quality assurance, and process management and their relationships. So these are the goals of the course. Now when it comes to the course outcomes, what you're going to get out of this course after learning the concepts of this course, what outcome, what's the main goal or the output which you're going to get? So we have this table which consists of the serial number, description, and RBT level. So basically, we have different levels for different descriptions, and there are 6 different descriptions, and their levels are given here. Now, there are 5 units in this course. Basically, Unit 1 deals with conventional software management, Unit 2 deals with improving software economics, Unit 3 is lifecycle phases, Unit 4 is workflows of the process, Unit 5 is project control and process instrumentation. And the textbook which is recommended is by Walker Royce, Software Project Management, Pearson Education. And these are the units you have to learn. Now, when it comes to the first unit, Conventional Software Management, I'll be discussing about the first and the second point. So the first point has 2 subdivisions. The first point is conventional software management. It consists of the waterfall model and the conventional software management performance. And the second point deals with evolution of software economics, which consists of, again, 2 subdivisions, 2.1, which is software economics, and 2.2, which is pragmatic software cost estimation. Now, the textbook, as I said before, is Walker Royce Software Project Management. Now, when it comes to conventional software management, conventional software economics provides a benchmark of performance for conventional software management principles. In conventional software management, the software development is highly unpredictable, okay? Only about 10% of software projects are dealt with successfully within initial budget and scheduled estimates. When it comes to the second point, which is management discipline is more of a discriminator in success or failure than our technology advances, okay? Now, the third point is the level of software scrape and rework is indicative of an immature process. Now, the tree analysis provides a good introduction to the magnitude of the software problem and the current norms for conventional software management performance, and there is much room for improvement. Okay, you must understand that conventional software management is the old methodology which has flaws, which is not perfect, and so, there is room for improvement. Now, the first point, which is 1.1, the waterfall model, we have again 2 parts, in theory and in practice. In theory, in 1970, Winston Royce presented a paper titled Managing the Development of Large-Scale Software Systems at IEEE WISCON, WESCON, Royce, Winston, 1970. Okay, so basically this paper presented 3 main points. Okay, the paper said that there are 2 essential steps which are common to the development of computer programs, which is analysis and coding. Okay, so analysis and coding, as you can see here in this diagram, from analysis we have to do the coding. Okay, analysis and coding both involve creative work that directly contributes to the usefulness of the end product. So very important thing, 2 essential steps common would be analysis and coding. And the second step would be, in order to manage and control all of these intellectual freedom associated with software development, one must introduce several overhead steps, including system requirements definition, software requirements definition, program design, and testing. So these steps supplement the analysis and coding steps, and this figure illustrates the resulting project profile and the basic steps in developing a large-scale program. So this is the diagram in which we have the system requirements, then comes software requirements, then comes analysis, program design, coding, testing, and operations. Okay? Now, the third point is that the basic framework described in the waterfall model is risky and invites failure. As I said before, there's scope for improvement, so it's risky and it invites failure. So sometimes these projects can fail, and the testing phase that occurs at the end of the development cycle is the first event for which timing, storage, and input-output transfers, etc., are experienced as distinguished from analyzed. And the resulting design changes are likely to be so disruptive that the software requirements upon which design is based are likely violated. Either the requirements must be modified or a substantial design change is warranted. So this is all about in theory, okay? And in theory, we have to understand that the waterfall model has some flaws, and there need to be improvements that need to be done. So 5 necessary improvements for this approach to work is, the first improvement is complete program design before analysis and coding begin. Okay, you have to complete program design. So you can't complete program design after you're done with analysis and coding. So you have to complete it beforehand. So first comes program design, then comes analysis, then comes coding. Okay, so complete program design before analysis and coding begin. And the second point is maintain current and complete documentation. So whatever project that you do, you have to maintain a set of documentation in which you have to write down in depth, in detail, about whatever has been done in that project, okay? So write in detail, explain it clearly, maintain current and complete documentation. And the third point is do the job twice if possible, okay? So do it n times, okay? You have to do it multiple times until the end user or the customer is satisfied. Don't do it once and try to fix the problem by yourself once. Do it twice, do it thrice, do it n times, and do the job twice if possible. If you have time, do it twice. Fourth one is plan, control, and monitor testing. Okay, you gotta monitor testing. Is one of the most important phases. So you gotta plan, control, and monitor testing. The fifth one is involve the customer. Customer is the one who's giving you the money, who's paying the money, right? So you need to satisfy the customer. So your goal is to make the customer happy, so involve the customer. So the first point, complete program design before analysis and coding begin. As I said before, the first step is to insert a preliminary program design phase between the software requirements generation phase and the analysis phase. By this technique, the program designer assures that the software will not fail because of storage, timing, and data flux. So the following steps are required. Begin the design process with program designers, not analysts or programmers. Okay? Design, define, and allocate the data processing modes. Write an overview document that is understandable, informative, and current so that every worker on the project can gain an elemental understanding of the system. The second point is maintain current and complete documentation. Document the design. The amount of documentation required on most software programs is quite a lot, certainly much more than most programmers, analysts, or program designers are willing to do if left to their own devices. Okay, if someone is left to themselves to do whatever they wanted to do, they will not focus on developing the code, which is required. Okay, which is the most important. Programming is the most important element, and so if you do leave someone to do things on their own, they will not program and they will not do the most important thing, okay? Because most people are lazy to do this. So why do we need so much documentation? So each designer must communicate with interface designers, managers, and possibly customers. The second point is during early phases, documentation is the design. The third one is the real monetary value of documentation is to support later modification by a separate test team and a separate maintenance team and operational personnel who are not software literate, okay? So that's why you have to create a documentation so that people who don't know anything about the project will still be able to understand what is written in this documentation. Okay, so even though they're not software literate, they still should be able to understand it. And the third point is do the job twice if possible. As I said, do it twice. If a computer program is being developed for the first time, arrange matters so that the version finally delivered to the customer for operational deployment. It's actually the second version insofar as critical design or operations are concerned. In the first version, the team must have a special broad competence where they are quickly sensing trouble spots, okay, in the design model, and then model alternative, forget the straightforward aspects of the design that aren't worth studying at this early point, and finally arrive at an error-free program. So do it n times approach. This is the principle of modern day iterative development. Okay, do it n times until the customer is satisfied. The fourth point is plan, control, and monitor testing. So without question, the biggest user of software resources, manpower, computer time, and management judgment is the test phase. Okay, test phase is most important because it deals with a lot of different things. And so if the test phase goes wrong, then everything related to this project is about a crash, and it's the greatest phase with greatest risk in terms of cost and schedule, because you're putting a lot of money here in the test phase, and so we want to ensure that the project gets accomplished quickly. And the three main recommendations were aimed at uncovering and solving problems before entering the test phase. However, even after doing these things, there is still a test phase, and there are still important things to be done, okay? Which includes employing a team of test specialists who are not responsible for the original design, employing visual inspection to spot the obvious errors, like dropped minus signs, missing factors of 2, jump to wrong addresses, test every logic path, employ the final checkout on the target computer. And so these are the points for planning, controlling, and monitoring testing. The final point is involve the customer. It's important to involve the customer in a formal way so that he has committed himself at early points before final delivery. And there are 3 points following requirements definition where the customer can bolster the development efforts. Okay, so these include a preliminary software review following the preliminary program design step, a sequence of critical software design reviews during program design, and a final software acceptance review following testing. Okay, so these 2 reviews have to be conducted so that the customer ultimately is satisfied. We get money from the customer, we have to satisfy and make the customer happy so that the customer keeps coming back. So involve the customer with early demonstrations and show the customer what you have done so far. Okay, and plan the alpha beta releases is a proven valuable technique which will help you to satisfy the customer. Okay, now I've discussed about theory. In practice, it's different. Waterfall model. In practice, the project destined for trouble frequently exhibit the following symptoms. So there are 5 symptoms, which are the symptoms exhibited by the project which is destined for failure or trouble. The first point is protracted integration and late design breakage. Second point is late risk resolution. The third point is requirements-driven functional decomposition. The fourth one is adversarial stakeholder relationship. And the fifth one is focus on documents and review meetings. Now, protracted integration, late design breakage is when, the progress of the project is not up to the mark, and as a result, something is not complete, and as a result, long time is taken for the project to get completed, and ultimately, because of that, the entire projects get failed. Okay, so progress is defined as percentage coded that is demonstrated in this target form. The following sequence was common: early success via paper designs and often too thorough briefings, and then commitment to code late in the life cycle. Integration nightmares due to unforeseen implementation issues and interface ambiguities, heavy budget and schedule pressure to get the system working, late shoehorning of non-optimal fixes with no time for redesign, very fragile, unmanageable product delivered late. Okay, so this is the first point. So this diagram shows where the late design breakage takes place. Okay, we have integration which begins, and then slowly we have the late design breakage taking place. Okay, so this graph includes the project schedule and the development progress, okay, percentage coded. So this figure illustrates the development progress versus time. Now, the second point is late risk resolution. Now, if risk is so important, right, we have to maintain and manage risk, and we have to take risk when it's needed. But at the same time, we have to be careful about the worst case scenarios of taking risk, right? So a serious issue associated with the waterfall lifecycle was a lack of early risk resolution. So we have to resolve all these risks early in the lifecycle so that we'll be able to successfully execute and do the project. So figure illustrates a typical risk profile for conventional waterfall model projects, and we have the project lifecycle here in x-axis and the project risk exposure on the y-axis. And then for requirements, design, coding, integration, testing, this is how the graph goes. Okay. Now, the third point is requirements-driven functional decomposition. Traditionally, the software development process has been requirements-driven. An attempt is made to provide a precise requirements definition and then to implement exactly those requirements. Okay, this approach depends on specifying requirements completely and unambiguously before other development activities begin. It naively treats all requirements as equally important and depends on those requirements remaining constant over the software development lifecycle. Now, these conditions rarely occur in the real world. Specification of requirements is a difficult and important part of the software development process, and so we need to be able to do this in an efficient manner. So that's why requirements-driven functional decomposition is so important, and this is why the projects fail. Okay. The fourth point is adversarial stakeholder relationship. Now, you need to maintain good relationship with the stakeholders of the project, and the conventional process tend to result in adversarial stakeholder relationships in large part because of the difficulties of requirement specification and the exchange of information solely through paper documents that capture engineering information in ad hoc formats. So the lack of rigorous notation resulted mostly in subjective reviews and opinionated exchanges of information. Now, there is no clear communication between the stakeholders, then definitely projects are bound to fail. And so this is why it's so important to have proper communication, proper meeting with the customer or the stakeholders of the project so that we'll be able to satisfy them. The fifth and last point is focus on documents and review meetings. Now, what's more important? You gotta get this job done. And for getting the job done, coding is important, and basically the user interface is important, testing is important, but what about documentation and review meetings? They are useless, okay? You just have a conference of people discussing about what I'm going to do, but then none of those people are, doing this thing. So what's the point in discussing, talking rather than doing? Okay, so the major milestones were actually implemented as ceremonious meetings. Okay, ceremonious meetings defined solely in terms of specific documents, but then they don't actually perform when it comes to implementation. Implementation is given more importance. So contractors were driven to produce literally tons of paper to meet milestones and demonstrate progress to stakeholders rather than spend their energy on tasks that would reduce the risk and produce quality software. Okay, you want to develop this quality software, it requires you to implement it correctly. So typically, presenters and the audience review these simple things that they understood rather than complex and important issues. So basically what happens is the audience do not understand these complex issues, okay? And so documentation itself is not good. So most design reviews therefore result in low engineering value and high cost in terms of effort and schedule involved in their preparation and conduct, and they presented merely a facade of progress. Now, I've discussed about waterfall model in theory and practice. Now I'll be talking about conventional software management performance. Barry Baum's one-page industrial software metrics top 10 list, which is Barry Baum, he actually in 1987, is a good, came up with this industrial software metrics top 10 list, which is a good characteristic observation of the state of the software development, and he mentioned 10 points. Okay, so these are the 10 points which he mentioned. Finding and fixing a software problem after delivery costs 100 times more than finding and fixing the problem in early design phases. The second point is you can compress software development schedules 25% of nominal, but not more. The third point is for every $1 you spend on development, you will spend $2 on maintenance. The fourth point is software development and maintenance costs are primarily a function of the number of those lines of code. The fifth point is variations among people account for the biggest differences in software productivity. Sixth point is the overall ratio of software to hardware costs is still growing. In 1955, it was 15:85. In 1985, it is 85:15. Seventh point is only about 15% of software development effort devoted to programming. The eighth one is software systems and products typically cost 3 times as much per SLOC as individual software programs. Software system products, that is system of systems, cost 9 times as much. Ninth point is walkthroughs catch 90% of the errors. 10th point is 80% of contribution comes from 20% of contributors. So these are the 10 points mentioned by Barry Bone in Industrial Software Metrics Top 10 list. Okay, so these are the points, which is a good objective characterization of the state of software development. Okay. Now, the 10th point, which I talked about, was 80% of contribution comes from 20% of contributors. This Pareto principle, okay, so 80% of engineering is consumed by 20% of requirements. We only have to focus on those 20% of things which you have to do, which will bring 80% of results, right? So we need to know about that. And 80% of software costs is consumed by 20% of competence. 80% of errors are caused by 20% of competence. 80% of software scrape and rework is caused by 20% of errors. 80% of resources are consumed by 20% of competence. 80% of engineering is accomplished by 20% of the tools, and 80% of the progress is made by 20% of the people. So conventional software management performance 1.2, 1.1 waterfall model. So this is all about this unit 1, subdivision 1, which is conventional software management. I hope you understood some concepts about software project management. If you have any doubts, leave it down in the comment section. I'll be able to answer it. Thank you so much for listening to this presentation.